All right, Calculus 12, we're at her again. We've just done derivatives of all of the trig functions. You should know them. You should have those 6 memorized down cold. Boom. So I'm just going to ask my son here right now. Keith, what is the derivative of sine?
I don't know.
Okay, well, he didn't listen to that lesson. Derivative of sine is cos. Allison, what's the derivative of secant? Okay, she doesn't know either. It's secant x tan x. But these are things you need to know. All the derivatives of sine, cos, tan, cosecant, secant, cotan. You need to have these memorized. So this will be, I'm going to fold the sheet over. This will be what you're going to have by your aid, by your side as an aid throughout these questions we're going to do today. So same units as last day, 7.2, 7.3. I didn't even assign anything last time. It was just to know these 6. Part 2 is now taking the derivative of all of these functions. So here's a whack of just random trig functions that are built with either ugly angles or product rules, quotient rules, and such. All right. So let's go through this guy here. So we've already done technically a quotient rule last time when we derived tan. So now we're going to go and look at, let's take the derivative. All of these want the derivative of this particular function. So you have to look at it, and this is just the beauty of trig now. You know everything you need to know. You know the first 5 chapters, all of the limits, product rules, quotient rules, chain rules, power rules, concavity, points of inflection, increasing, decreasing, derivatives, tangent lines. All of that is now just rolled in with trig. So here we go. We look at this, it wants the derivative. You look at that and say, okay, which rule do I have to invoke here? Well, first of all, sine of 7x. This is not a time symbol in here. Remember, this is inside this function. So this is going to be a chain rule. So when you see the chain rule, you have to remember, what's a chain rule? The chain rule is the derivative of the outer function evaluated at the inside times the derivative of the inside. Don't forget the baby. So let's go through this. This is the outer function. This is the inner function. So derivative is the derivative of the outer function. What's the derivative of sine? Cos. So it's going to be cos. Keep the inside the same, but then you got to multiply by the derivative of the inside, which remember I called the baby. So that's going to be 7. And to make it look pretty, that's 7 on the back end. It's not inside anything. I'm just going to put the 7 out front. Now your book has a really weird tendency of, they won't put the brackets around this, but I really prefer that because I see the inside. So as soon as, if your book writes sine of 7x, that really means that. That might be a wise thing to do. So there's our first answer. Next one, I look at this and say, okay, what do I have? Cos of this. Well, this is inside that. This is another chain rule. This has got the outer, this is the inner chain. So chain rule is outer derivative. What's the derivative of cos? Negative sine. Inside stays the same. I must multiply by the derivative of the inside, and the inside derivative of this is 14x, using the old skills you have before. And then making it look a little prettier, I'll pop this 14x out front with the negative. Just that's a little bit more convenient looking. There's my derivative. So you know all of this. It's just now a matter of recognizing what you have. And that's the hardest part at first, and you'll make mistakes as you're doing it. Next guy, tan of 5x squared. Again, this is inside this function. This is another chain rule. Outer, inner. So chain rule. What's the derivative of tan? Oh man, I should know it, but I do. Tan derivative is secant squared. But you keep the inside the same. I know on here, the derivative of tan is secant squared x, but this angle has to be copied with the chain rule. But then where the difference is, you got to multiply by the baby. Derivative of 5x squared is 10x. And there's our answer cleaned up a little bit. Alrighty. Next guy. Y equals sine cubed x. So this cube Now I gotta be careful. This is not inside with the x. I personally prefer to write it like this. I write it like that for convenience, but I write it like this for my derivative taking. And now I look at that and go, oh, this is a chain rule, where this is the outer and this is the inner. And there's nothing, there could have been another inner, but that's a simple x on the inside, so it's kind of one layer of chain rule. So here comes chain rule again. So outer derivative. Outer derivative is, just like you would for a polynomial in here, the 3 comes down, inside stays the same, lowers by 1, there's the mama. And the baby is the derivative of sine. What's the derivative of sine? Cosine. And there's your answer. The back of the book will probably rewrite this with the squared here. And then you might even do some trig identities on this if you want. I don't feel like it. Don't need to. There's an answer. Back of the book might, and you might have to then check to see if they're the same. Next one, sine of x times cos of x. Well, there's nothing inside this sine except for a regular x, nothing inside that cos. This is a product. So out comes your good little product rule. First function times the derivative of the second. I'm going to write it out without doing it yet. Plus the second function times the derivative of the first. So you get sine of x times derivative of cos, negative sine. Derivative of sine, cos. And then you end up with the derivative equaling negative sine squared x plus cos squared x, or cos squared x minus sine squared x, which could be, that could even be a double angle identity, or an angle, or it could be, if you go to your trig identity sheet, that could be changed to something else. I'm going off the top of my head. I think, I could be wrong. I think that's the double cos, one of the double cos identities. I'd have to look into that though. I don't have my sheet in front of me. So the answer in the back could be this, could be that, if that is true. My mind is not as blank on that one. Next guy, secant of 5x. So I look at it again. Is it a product rule? No. Is it a quotient rule? No. Oh yeah, it's definitely got a outer function and an inner function. Good old chain rule. So my derivative would have to be outer function. Now the derivative of secant x is secant x tan x. The derivative of secant is going to be secant something tan something, and the something here, because of chain rule, that has to stay the same. Because remember, it's the outer derivative evaluated at the inside times, so there's the mama, because that's the rule. The baby, derivative of 5x is 5. And making it look a little prettier, there you go. Alright, so that's all the derivative rules that you've learned. The quotient rule wasn't in here, but we did that the other time. We would just do the same thing if you had a quotient of trig. You would do the quotient rule and clean it up with your algebra skills. More derivatives, good times, because then you just get more layers. So look at this mess. It is a mess. That's an ugly trig function. When I see the cube here, my first thought, I'm not even going to take the derivative. I'm just going to rewrite this personally like this, because then I can see the layers of how this is built. With that cube there, it's nice for writing, but poor for analyzing. So what do I have? Well, I have basically layers. This is my outer function, this is my inner function, and then within that inner function I've got another inner function. So this is basically like a big chain rule. So let's just start peeling off the layers. So outer function derivative, the 3 comes down, multiplies the 2 and gives you 6. Inside stays the same, as ugly as it is, lowers by 1. Now I need to take the derivative, and I'll just do this in stages. I need to take the derivative of the inside. which as you get good with this, you can do it, but I'm just doing this in stages. So there's, I'm just going to rewrite this part here. So if you're doing it in stages, a lot of rewriting. So what's the derivative of this? Oh, another chain rule. So outer derivative. What's the derivative of cosecant? Oh man, I got to know that. Negative cosecant cotan. So negative cosecant cotan. Oops. Shoot. Cotan. Inside stays the same. That's the most important piece that people miss. So there's the outer derivative, evaluated at the inside. Then I got to times by the last baby, the derivative of the inside, 6x. And that's just a rat's nest, because remember, there was the outer layer, the mama. Then there's the baby, and the baby has its own mama and baby. And if I clean this up, so negative 6 and 6, so negative 36. I would prefer to put this x out front. I would then also prefer to write this cosecant as a squared here. And then I got another cosecant and a cotan. And by fluke, these are both the same, so I can write them as a cube. A lot of rewriting sometimes. A lot of practice on this. You just gotta build your confidence. And there would be your derivative. Now just, even though that's a lot of thinking, imagine doing that with limits. I'd run away crying. Okay, B. What do we got? You got cosine, and inside the cosine is a cosecant, and inside the cosecant is a 5x. Again, this is another chain rule. And then we got to peel off the layers. Everything's written well. So, outer derivative. Derivative of cosine. Negative sine. Inside stays the same. But then I got to multiply by the baby. I got to multiply by the derivative of that. But at least one layer is peeled off. The outer layer, you're done. Rewrite it. Derivative of this now. Okay, it's another inside out, outside inside. So outside derivative, derivative of cosecant is negative cosecant. Evaluated at the inside, cotan, evaluated at the inside. Times the last baby, which I could write the derivative of 5x, but I'm going to just do it. Derivative of 5x is 5. 3 layers again to that particular derivative. Cleaning it all up, negative, negative, and 5. I'd put the 5 out front. I have sine of cosecant 5x, and that cosecant 5x is inside the sine, multiplied by a separate cosecant 5x, which is not even inside at all, it's just multiplying it. So notice here, these cannot be joined together because this is inside the sine, and there's my weird and ugly derivative. Now, let's say the back of the book I didn't have one. I could go to Desmos, I could graph this, call it f of x, then I could do the derivative function with Desmos and see the graph and then type this in, and if they're not the same, I know I would messed up. Okay, last example on this page, then we got one more to go. When I see this horrible mess, first of all, I'd be tempted to graph that in Desmos because this would just be an absolute gong show. When you see not y isolated, this screams implicit. So now good old implicit comes out. Okay, well, implicit, I know how to do that. So I'll take the derivative of sine y. If that was sine x, the derivative of sine would be cos. So the derivative of sine y is cos y, but you have to multiply by the derivative of the inside. And remember, if it's not in terms of x, you multiply by dy dx. Plus the derivative of cos 3x. Well, there's no tricks there except for there's a chain rule. Outer derivative, sine, multiplied by the baby, the inside 3. Derivative of tan 2y. Just pretend for a moment that was x. The derivative of tan would be secant squared of 2x, in this case 2y. But then I have to multiply by the derivative of the inside. What's the derivative of 2y? Well, it's 2 times dy dx. And plus the derivative of 7, that's the only happy part, is 0. Once you've done that, that's the hardest part generally, is people miss the dy's, dx's, is now you want to get all the dy dx's to one side. So what I'm going to choose to do is I'm going to move this over here and this over here, so I end up with this. Making this look a little prettier, I'll put the 2 out front. Dy dx, I'll move this to the other side, it becomes positive, pop the 3 in front. Factor out a dy dx, because this is standard now. Standard process, just trig in the mix. And my last little step, divide both sides by this mess. So you end up with 3 sine of 3x all divided by cos of y minus 2 secant squared of 2y. Holy Toledo. There it is. Alright, so it takes a lot of work, a lot of practice, but these are important skills that in university your prof will just blow through. Like, they won't even take the time to do very many examples, to be honest. It'll just be, oh, you already know all your chain rules and quotient rules and implicit. You now know your trig rules, go and do it, have fun. Last example is this guy here, which is find the tangent line equation. Okay, you've done that. As soon as I see that, I'm like, boom. Tangent line equation, there's my tangent, or there's a line. I need the slope, and the slope will be the derivative evaluated at the point of interest, and then I'll have the point, which is x1, y1. So I just need to get from this equation the slope and the point. So it doesn't matter what I do first. Let's do slope just because we're doing calculus. So slope is going to be the derivative of this function evaluated at, they told me, at pi over 6. Okay, so the derivative, that says quotient rule. Bottom times the derivative of the top, derivative of sine, is cosine minus the top times the derivative of the bottom. The derivative of cosine 2x is negative sine 2x times the baby, all over the bottom squared. Now I might do a little bit of cleanup. I'm not going to do much, to be honest. Double negative there, so positive 2 sine x. And I could do some identities, but you know what? I'm going to be evaluating it anyway. I don't feel like making my life difficult. Now I need to evaluate that at pi over 6. So I'll go and plug pi over 6 into all of these. So cos of, now 2 times pi over 6. When I plug pi over 6 into and multiply it by 2, I get pi over 3. That is pi over 6 as it is. This is sine of pi over 6. This is sine of pi over 3 because I'm doubling it again. And the bottom, let's write the squared this way. I'm doubling the angle as well, so that's cos of pi over 3 all squared. And now here comes your pre-calc 12 out again. So cos of pi over 3, that's cos of 60, is 1/2. Cos of pi over 3 is root 3 over 2. Sine of pi over 6 is 1/2. Cos of pi over 3 is root 3 over 2. All over cos of pi over 3 again is 1/2, and 1/2 squared is 1/4. So looking at this, before I get excited, I can see that this is going to be root 3 over 4. I could cancel out these 2's, but you know what? Because this is already a 4, I'm going to keep this as a 4 because I'm going to get 2 root 3 over 4, just more convenient. And now I end up with, because I can get these together with a common denominator, I end up with 3 root 3 over 4 over 1/4. When I flip and multiply, that 1/4 cancels out this, and I get 3 root 3. So now at least I know my slope. I know my slope at pi over 6 is 3 root 3. All that work for that. And then my last little step here, that's the hardest part, is the point. The point, remember, is pi over 6, f of pi over 6. So I need to plug pi over 6 into the original function, and you get sine of pi over 6 over cos of pi over 3. Cos of pi over 6. Sorry, my table's jiggling. Sine of pi over 6 is 1/2. Cos of pi over 3 is 1/2. Oh, the point is pi over 6 comma 1. So now finally, here's my final stage. My tangent line must be y minus 1 equals the slope 3 root 3, which we worked out earlier, minus x minus pi over 6, because that's the x value. Whew! Good times. All right, we're going to stop there. Have a good day. Talk to you soon.